Hi, welcome to Why Bayes Theorem is Important, Part 3b. So this video is a continuation of the video Why Bayes Theorem is Important, Part 3a. This video will assume that you've watched that video and pick up where it left off. So if you haven't watched that yet, you should check it out before continuing here. In Part 3a, we saw that we ran into difficulties when trying to evaluate the probability of the hypothesis that the number of expected decays in a radioactive sample over 10 minutes, lambda, was equal to 2500. We decided to instead consider the revised hypothesis that lambda was between 2500 and 2501. So let's try to evaluate the probability of this hypothesis given that the observed number of decays m was 2553. So that's the probability that lambda is between 2500 and 2501 given that m is equal to 2553. Now, there will be quite a bit of math in this video. Before we go through all this work, it's good to remind ourselves of what we're trying to accomplish here. When we do a measurement, we're trying to learn about the true value of the quantity we're measuring, in this case, lambda. But measurements have uncertainties, so the measured value will not perfectly coincide with the true value of the parameter. So we might want to ask for the probability, given the result of the measurement, that the true value of the parameter lies in some range. Strictly speaking, however, the measurement alone doesn't answer this question. We need to use Bayes' theorem, and Bayes' theorem requires the input of prior probabilities, the choice of which is subjective. Now, while the choice of prior will affect our result, its effects on our conclusions about which ranges of the parameter are likely won't be very large as long as we limit ourselves to reasonably well-behaved priors and our measurement uncertainties are small. So while we must choose a prior, if our data are good enough, the prior probably won't matter very much in the end. Discussions of these issues can be hard to find, and when they are found, they tend to be confusing. These issues can lead to somewhat cryptic-sounding statements, like if a parameter is measured and a 95% confidence interval is quoted as the result, that does not mean that the probability that the true value is within that interval is 95%. Unfortunately, statements like this are rarely accompanied by good explanations. Now, we won't explicitly be talking about confidence intervals here, but we'll hit on these same issues that lead to confusing statements like that above. So we're going to go through some of the gory detail here. The hope is that by going through this in detail, we can elucidate some subtle issues that are rarely explained well. Okay, so with that, let's get back to our evaluation of the probability that lambda is between 2500 and 2501 given that m is equal to 2553. Okay, so we'll use Bayes' theorem on our revised hypothesis to get the probability that lambda is between 2500 and 2501 given that m is equal to 2553. So Bayes' theorem tells us that that is equal to the probability that m would equal 2553 given that lambda was between 2500 and 2501 times the probability that lambda is between 2500 and 2501 divided by the probability that m would equal 2553. So to get the probability that lambda is between 2500 and 2501, given that m equals 2553, we have three factors we must evaluate on the right-hand side of this equation. Let's start with the probability that m equals 2553 given that lambda is between 2500 and 2501, a factor in the numerator on the right-hand side. Now, if we had a single value for lambda, we'd know what to do. The probability to observe m events when lambda are expected on average is given by the Poisson distribution, here shown using a Gaussian approximation. So, for example, for lambda equal to 2500, we could just substitute 2553 for m and 2500 for lambda. Here, however, we don't have just a single value of lambda. We have a range, 2500 to 2501. However, this range is pretty small. Maybe we'll find that it's small enough we can act like it covers just a single value of lambda. So, to estimate the probability that m equals 2553, given that lambda is between 2500 and 2501, let's calculate the probability that m would equal 2553 given that lambda equals 2500, and the probability that m would equal 2553 given that lambda equals 2501. So, to get the probability that m would equal 2553 given that lambda equals 2500, we substitute m equals 2553 and lambda equals 2500 into the Poisson probability equation. This gives us that the probability that m equals 2553 given that lambda equals 2500, which is just the Poisson probability, is approximately 0.0046. Okay, now let's get the probability that m would equal 2553 given that lambda is equal to 2501. This means getting the Poisson probability for m equals to 2553 and lambda equal to 2501. If we substitute m equals 2553 and lambda equals 2501 into our Poisson probability formula, we get that the probability that m equals 2553, given that lambda equals 2501, is also approximately 0.0046. Now, while they are not equal, within the precision that we're working at here, the probability that m would equal 2553, given that lambda is equal to 2500, and the probability that m would equal 2553, given that lambda is equal to 2501, are both 0.0046. The same will be true for all values of lambda between 2500 and 2501. So it's safe to take the probability that m would equal 2553 given that lambda is between 2500 and 2501 as approximately equal to 0.0046. Okay, so now we have one of the three factors that we need in our Bayes theorem equation. So let's start working on the other two factors in our equation, the second factor in the numerator and the factor in the denominator. We'll start with the factor in the numerator, the probability that lambda is between 2500 and 2501, because having that in hand will help us to get the other factor, the probability that m would equal 2553. Okay, so the probability that lambda is between 2500 and 2501 is the probability that you would want to assign to the hypothesis that lambda is between 2500 and 2501 without knowing anything about the value of m. It is a prior probability. There is no one right answer to this, but we have to choose something. We'll pick a particularly convenient prior and work out the result. Afterwards, we'll discuss what would happen with other choices. Okay, so let's see what we can say about the probability that lambda is between 2500 and 2501. While you don't know too much about the sample because there are no records, you do know a few things. First of all, you know that lambda is greater than 0 because the expected number of decays cannot be negative. You also know that the museum's exhibit was designed to display counts as they came in, so you don't think the museum would use a sample that gave more than about 10 counts per second. Now, 10 counts per second would correspond to 6,000 counts in a 10-minute interval, so you think lambda is probably less than 6,000. But to be on the safe side, you decide to make the slightly weaker assumption that lambda is less than 10,000. So you consider 0 to 10,000 to be the reasonable possible range for lambda. Now we have to think a little harder about what to take for the probability that lambda is between 2500 and 2501. Okay, so let's do the following. Let's take all values of lambda between 0 and 10,000 as equally likely. Note that nothing requires us to assume all values equally likely. This is a choice we make, and other sets of assumptions are possible. One way to do this is to divide the range 0 to 10,000 into 10,000 bins and take each of these bins as equally likely, each with a probability of 1 over 10,000. Okay, so we're taking the probability that lambda is between 0 and 1 to be equal to the probability that lambda is between 1 and 2, which is in turn equal to the probability that lambda is between 2 and 3, etc., which are all equal to the probability that lambda is between 2500 and 2501, and which are also equal to the probability that lambda is between 9999 and 10,000. We're taking each of those probabilities to be 1 over 10,000. Okay, so now we have a value to assume for the probability that lambda is between 2500 and 2501. That value is 1 over 10,000. In addition to being simple, this assumption is one that many people would find intuitive, as it doesn't favor any particular value of lambda in the range between 0 and 10,000. However, it is important to remember that this is still an assumption. We'll come back to this point after the calculation. Okay, so now we have 2 of the 3 factors in our equation, but we still need the factor in the denominator, the probability that m is equal to 2553. So this is the probability of observing m equals 2553 evaluated without knowing what lambda is. Now, while the probability of m equals 2553 is evaluated without knowing the value of lambda, it is evaluated using the same assumptions about the prior probability distribution of lambda that we made when getting the probability for lambda to be between 2500 and 2501. We assumed that all values of lambda between 0 and 10,000 were equally likely and values outside this range were disallowed. Okay, so we will get the probability for m to equal 2553 in 2 ways. First, we'll argue that the probability that m equals 2553 must be very, very close to 1 over 10,000. Next, we'll show that it is within a reasonable approximation. Okay, so first, the argument. We've taken lambda flatly distributed between 0 and 10,000. In other words, the probability of lambda falling into any particular bin in this range is the same for all bins. While m is determined probabilistically, for a given value of lambda by the Poisson distribution, the distribution is sharply peaked around lambda. In other words, values of m very close to lambda are much more probable than values of m far from lambda. So we expect m to be distributed much like lambda is. As lambda is taken to be flatly distributed between 0 and 10,000, we expect m to have a probability distribution close to this. Now we should note that this will not be exact, as m can still take on values above 10,000, but it should be very close as long as lambda doesn't get too close to its upper limit of 10,000. As m was observed to be 2553, lambda is almost certainly much less than 10,000, so this approximation should be fine. Okay, so that was the argument. Now let's show it more mathematically. What we want is the probability that m equals 2553. If we knew lambda, we could calculate the probability of getting m events using the Poisson probability. But alas, we don't know lambda. However, while we don't know lambda, we do have a probability distribution for lambda. We said that lambda was between 0 and 10,000. We divided this region into 10,000 bins. We said that the true value of lambda was equally likely to fall in any of these bins, so the probability of lambda falling into any particular bin was 1 over 10,000. Let's say we wanted to get the probability that m equals 2553 and lambda was between 2400 and 2401. We'd multiply the probability that lambda was between 2400 and 2401, that's 1 over 10,000, times the probability that m equals 2553, given that lambda is between 2400 and 2401. So the probability that m is equal to 2553 and lambda is between 2400 and 2401 is equal to 1 over 10,000 times the probability that m would equal 2553 given that lambda was between 2400 and 2401. Now, the probability that m equals 2553, given that lambda is between 2400 and 2401, is going to be between the probability that m equals 2553 given that lambda equals 2400, which is just the Poisson probability for m equals 2553 and lambda equals 2400, and the Poisson probability for m to equal 2553 given that lambda equals 2401, which is just the Poisson probability for m equals 2553 and lambda equals 2401. But these will be very close to each other in value, so let's just approximate the probability that m equals 2553 given that lambda is between 2400 and 2401 as the Poisson probability for m equals 2553 and lambda equals 2401. Thus, our expression for the probability that m equals 2553 and lambda is between 2400 and 2401 becomes the probability that m equals 2553 and lambda is between 2400 and 2401 equals 1 over 10,000 times the Poisson probability for m equals 2553 and lambda equals 2401. We can do the same thing for any other bin that lambda can fall in. To get the probability that m equals 2553, we can write down this expression for a given bin and then add up the contributions of all 10,000 bins. So the probability for m to equal 2553 is equal to the sum over all 10,000 bins of lambda of 1 over 10,000, that's the probability for lambda to fall in any given bin, times the Poisson probability for m equals 2553 and lambda equals, well, lambda. And again, we approximated lambda as constant over any given bin. Now, this expression probably looks like a pain, but it won't be too hard if we make some simplifying approximations. Let's take another look at the Poisson probability to observe a given value of m evaluated for a general value of lambda. So here again is the Gaussian approximation for the Poisson distribution. Now first, let's note that for any value of lambda, if we sum the Poisson distribution over all possible values of m from 0 to infinity, we must get 1. This is because some value of m must occur in any observation. If we add up the probabilities for all values of m that we could observe, we must get 1. So summing over values of m isn't too bad. The sum over m from 0 to infinity of the Poisson distribution of m and lambda is equal to 1. However, what we actually want to do is substitute in 2553 for m and sum over lambda. So we had that the probability for m to equal 2553 was equal to the sum over lambda from 1 to 10,000 times 1 over 10,000 times the Poisson probability for m equals 2553 and lambda. So let's take a look at the Poisson distribution for m equals 2553 and general lambda. We show the expression here. This is largest in the region lambda is approximately 2553, and it gets really small as lambda gets far away from 2553. Specifically, the factor e to the minus 2553 minus lambda squared over 2 lambda gets very small for the case where 2553 minus lambda, absolute value, is greater than a few times the square root of lambda, which is a few times the square root of 2553, which is a few times 51. So we really only need to look at the Poisson distribution for m equals 2553 and general lambda in the region where the absolute value of 2553 minus lambda is less than a few times 51, because it is very small elsewhere. Let's see how this expression behaves in this region. The fractional change in lambda between 2553 minus a few times 51 and 2553 plus a few times 51 is pretty small, a few percent. This means that the square root of lambda in the denominator and the 2 lambda in the exponent don't change very much. But while lambda doesn't change very much, 2553 minus lambda in the exponent does change a lot, as lambda varies between 2553 minus a few times 51 and 2553 plus a few times 51. We can capture the main behavior of this expression but make it much easier to deal with if we approximate lambda as about 2553 in the two places where its exact value doesn't matter very much. So now we take our Poisson probability for m equals 2553 and a general lambda, and we substitute in 2553 for two of the instances of lambda in this expression, the one in the denominator of the factor up front and the one in the denominator of the exponent. Now let's use this in our expression for the probability that m would equal 2553. So the probability that m would equal 2553 was the sum over all bins of lambda from 1 to 10,000 of 1 over 10,000 times the Poisson probability for m to equal 2553 and general lambda. So this is approximately equal to the sum over those 10,000 bins of 1 over 10,000 times our expression for the Poisson probability where 2553 has been substituted in for those two values of lambda. And then finally, in the last line on the slide, we've just taken that factor of 1 over 10,000 and put it out front. Okay, so we have our approximate expression for the probability that m would equal 2553. Let's compare that to what we saw earlier, that the sum of the Poisson probabilities over m from 0 to infinity for any value of lambda equals 1. Now, these sums are almost the same, except that lambda and m have reversed roles. So in our second expression, we have a sum over m, and lambda is a constant. In our first expression, we have a sum over lambda, and m has been replaced with the constant 2553. So if we look at these two expressions, we see that the sums are almost identical except for the role reversal. Now, there is one difference still remaining. The sum in the probability that m equals 2553 is from lambda equals 1 to lambda equals 10,000, while the sum in the other expression is from m equals 0 to m equals infinity. However, only terms where the exponent is approximately 0 are of non-negligible size. So the fact that one sum is from 1 to 10,000 and the other is from 0 to infinity makes very little difference in the sums. So we can use the previous result, that the sum over m from 0 to infinity of the Poisson probability for m and lambda is equal to 1, to see that the sum in our probability for m to equal 2553 is approximately 1. So the probability for m to equal 2553 is approximately equal to 1 over 10,000, as argued before. Now, our calculation here of the probability that m would equal 2553 has been somewhat rough. However, if we started with the exact Poisson probability for m to equal 2553 for general lambda and did the calculation exactly, we would find that the result, the probability of m to equal 2553 equals 1 over 10,000, is actually extremely close to the correct value. Okay, now we're ready to go back to Bayes' theorem. Okay, so with our newfound value for the probability that m would equal 2553, we can finally use our Bayes' theorem relation. So that was that the probability that lambda was between 2500 and 2501, given that m equals 2553, is equal to the probability that m would equal 2553 given that lambda was between 2500 and 2501, times the probability that lambda would be between 2500 and 2501, divided by the probability that m would be 2553. So we had the following three values. We had that the probability for lambda to be between 2500 and 2501 was equal to 1 over 10,000. And the probability for m to equal 2553 was also 1 over 10,000. However, we had that the probability for m to equal 2553, given that lambda was between 2500 and 2501, was approximately equal to 0.0046. So this gives us that the probability that lambda is between 2500 and 2501, given that m equals 2553, is approximately 0.0046. Now note that with this flat prior, we had that the probability for lambda to be between 2500 and 2501, given that m was equal to 2553, was equal to the probability that m would equal 2553, given that lambda was between 2500 and 2501. We could also have evaluated this for other values of lambda. So the probability that lambda is between n and n plus 1, given that m is equal to 2553, is equal to the probability that m equals 2553, given that lambda is between n and n plus 1, as long as n is not too far from 2553. So we get that the probability that lambda is between n and n plus 1, given that m equals 2553, is equal to the probability that m would equal 2553, given that lambda is between n and n plus 1. And that's just the Poisson probability for m equals 2553 evaluated for lambda equals n. And here we have made the approximation that n and n plus 1 are not too different. Okay, so we have our result from the previous slide. So after your measurement, the probability distribution for lambda is well described by a Gaussian with a mean of m equals 2553 and a standard deviation of sigma equals the square root of 2553. The most likely value for lambda to take is the observed value, 2553, and sigma is the same as the uncertainty on the measurement. Now, this result might seem intuitive. However, this result depended on two things. One, the measurement uncertainties were Gaussian, and two, the assumed prior probability distribution for lambda was flat in the region of the observed value. So the probability for lambda to be between n and n plus 1 was constant in the region around 2553. And also, the prior probability distribution for lambda was not substantially larger in some other region. Now, Gaussian measurement uncertainties are by no means universal, but they are quite common, so our first assumption isn't exactly unreasonable. But let's talk about our second assumption, our choice for the prior probability distribution for lambda. So the first thing to point out about our choice for the prior is that while it might be a very reasonable assumption, it is still an assumption and it does affect our final result. As a demonstration that this assumption is non-trivial, let's imagine you are measuring some physical parameter, which we'll call alpha. Let's say you think alpha can range from 0 to 10. You might think that taking all values of alpha between 0 and 10 to be equally likely is a reasonable assumption. This would mean, for example, that you believe the probability for alpha to be between 0 and 5 is the same as the probability for it to be between 5 and 10. However, let's say that you're interested in using your value of alpha for some purpose. Let's say it comes into some useful formula which uses not alpha itself, but alpha squared. If you take the probability for alpha to be between 0 and 5 as the same as the probability for it to be between 5 and 10, that's assuming that alpha squared is equally likely to be between 0 and 25 as it is to be between 25 and 100. So taking all acceptable values of alpha to be equally likely is not the same as taking all values of alpha squared to be equally likely. The latter option would mean assuming that alpha squared is equally likely to be between 0 and 50 as it is to be between 50 and 100. So you might end up asking yourself, do you want to assume that all acceptable values of alpha are equally likely, or that all acceptable values of alpha squared are equally likely? So while the flat prior that we've used here is simple, it's important to understand that it is an assumption, and a non-trivial one at that. When might we specifically want to use a non-flat probability distribution for a prior? A common scenario in which this arises is if you do more than one measurement. For example here, let's say you decided to measure the rate of counts from your sample again. So you decide to put the sample back in the apparatus and, this time, wait for 20 minutes. However, you don't want to throw out the information from your first measurement. After your first measurement, you have a probability distribution for lambda. It is a Gaussian centered at 2553 with a standard deviation of sigma equal to the square root of 2553. You can use this probability distribution as the prior for your second measurement. So in order to calculate the probability of a certain hypothesis, you must start with a prior. At this point, it might be somewhat unnerving that evaluating the probability of a hypothesis involves initial assumptions that are subjective. And while that's true, the situation may not be as dire as it initially seems. So first, let's note that if we had instead taken a different initial probability distribution for lambda that was still reasonably well behaved and was flat in the region between 2553 minus a few times 51 and 2553 plus a few times 51, we would have gotten pretty much the same result. So if we had taken lambda as flatly distributed between 2000 and 3000, or between 2200 and 6800, or between 2300 and 2800, our result would have been almost identical to the one we got. Also, if you have to choose between multiple sets of reasonable priors, and your conclusions depend on which set of priors you choose, you can mitigate this problem by getting better data, in other words, reducing the size of your measurement uncertainty. So although you must choose a prior, if your data are good enough, which prior you choose won't matter for figuring out the most probable parameter value in the end. Okay, now let's summarize. Here we've taken a look at what a measurement and its uncertainty imply about the true value of the measured parameter. We looked at applying Bayes' theorem to assign probabilities to the hypothesis that the true value of a physical parameter falls in a certain range. We saw that doing so requires assuming an initial set of probabilities, called priors, for the value of the parameter in question. We also saw that, in the case of Gaussian measurement uncertainties and a flat prior, the probability distribution for the true value of the parameter is just a Gaussian centered at the measured value with a width given by the measurement uncertainty. However, the choice of prior has no correct answer and is subjective. While the chosen prior does affect the final probability assigned to a hypothesis, the need to choose a prior does not make the result meaningless. As long as the prior distribution is reasonably well behaved, what matters is its behavior in the region within a few times the measurement uncertainty of the measured value. Improving the quality of one's measurement, in other words, reducing the size of the systematic uncertainties, can mitigate the effects of the choice of prior.